I'm trying to make myself feel better, goddammit. But you see, I get up to 82 then, which is an extra 10 years, so I'll take what I can get. I guess we should start again. I was just sitting here messing around.
It's based on your birth, not where you live in.
Yeah, I'm sure. Okay, so moving on. Where were we? So that's one data set. Let's go back to our other data set that we were playing around with yesterday, which is our fuel economy data set. Just so that you get a little bit of a generalizability of what you're learning.
So now you're wiping everything.
Now I'm wiping everything. And I'm going to load up the fuel economy package. Leah, did you install the fuel economy package?
I think I need to redo it because I'm trying to save everything separately.
Okay, because you only need to install the package once.
Oh, okay. Then I need.
So try library, fuel economy. And if you don't get an error, it should be saved. Good. And the data set we want out of that is the vehicles data. So that should put a vehicles object up in your data, and it doesn't, for some reason it doesn't load up until you do something with it. And let's go back to our question about the about that we ended yesterday on, about why our model comparing VW and Audi directly wasn't a good model, and why there might be some sort of intervening thing going on that was getting in our way, getting in the way of our inference. So let's backtrack to where we were yesterday so we can catch up again and make the same data frame. Feel free to copy and paste your code from yesterday, but I'll do this anyway. So we've got a subset of vehicles where make is equal to Audi. And here do an AND, right? Because you want logical. So we're pointing at two things together. Class is equal to mid-size cars. So now we've got all the Audi mid-size cars, the data frame just for them. Not the same thing for BMW, for VW. And we won't plot it all out again. Or while Leah's catching up, we'll plot it out again using code from yesterday. Oh, that's right. Yeah, we want to make our data frame again called mid. Try to be consistent with mine. Sorry, I just have very little space here. Try to be consistent with our labeling. So that's made the same data frame as yesterday.
I'm trying to combine picking out the audio and Volkswagen cars
Yeah.
in one sentence
Yes.
with or.
Yep, that'll be the way to do it.
Yeah, but it gives me the wrong number.
You might
So
need to...
make equals to Volkswagen or make equals to oh.
Yeah.
That is
So it needs to be... Yeah.
two things. I have Volkswagen twice. Maybe that's it. Yeah, that's it.
Yeah, that's a more efficient way to do it. I'll just wait till everyone's caught up. And I can see I'm not being consistent in my labelling, so I'll go back to my consistent labelling. Sorry about that. But I'll make these plots again. So just cut and paste that over from yesterday. Essentially what we'll do is we'll make this density. Yeah? Oh yeah, we don't have a correlation table coming, so I don't need to do that, I guess. I've been leaving it like that for the linear models. So what I've done here, load the fuel economy, pick out the data, vehicles data, define Audi mid-size vehicles, define VW mid-size vehicles, make a data frame called mid-size cars using Carbind, calculate the density of the city fuel efficiency for Audi and the density of the city fuel efficiency for VW. Define our see-through colour like we did the other day, and then plot the densities using the see-through colour. And I have to evaluate it all, otherwise no way. Okay, and this is not essential for the linear modelling, it's just to get us back to where we were yesterday. We'll do the linear modelling separately, but just to remind you where we were, we had the problem here that maybe just a normal distribution defined by each car is not an appropriate model of the data, because we've got these bumps out here, and what could be causing these bumps? And then we realised when we looked at the data that it could be the number of cylinders causing these bumps. So we made a new plot to explore that, which was just a simple scatter plot with a bit of jitter in it. Remember, the jitter just adds noise. Number of cylinders, so how big's the engine? And the city fuel efficiency. And we saw that as the number of cylinders increases, the fuel efficiency goes down. And that happens for VW too. So that tells us that there's something important going on here. That tells us that there's not just the car that's caused the type of car that's causing a difference in fuel efficiency, or that's related to is related to fuel efficiency, but also some other factor that's in the data set, and that other factor we've gone exploring for and we've found is the number of cylinders in the car. So that's where we got to yesterday. And now we can make a linear model about that. So are you caught up roughly, Leah? Are you okay?
My computer's a bit short-circuiting, so no, not at all.
Is it starting? Or?
I'm trying to shut Word down and that finds it very old, so it's
Oh,
not going
yeah,
good.
it's just ours not loading anything because
It's
the
not.
process isn't
Okay.
done.
So all we're going to do now is a linear model anyway, so just follow along conceptually.
Yeah.
You're not missing anything if you can't sit and type it. So let's start to look at that, and let's start to see if we can test that as our hypothesis or estimate that effect. So what we're going to do now is we're going to look at something called an interaction between variables. So before, when we analysed sort of multiple variables at once, we calculated, say, the effect of the car driving east, or the component of the eastward movement of the car relative to the northward component. And then we look separately at the vertical component relative to the northward component. But we didn't look at the interaction and the relationship between the vertical component and the eastward component, and the effect of those two combined on the northward component. And now we're going to do that. So what you can think of as what we're doing here is we're looking at not just an effect, say the effect of make on car, or the effect of cylinder on car separately. We can do that. We're also, after we've done that, going to go in and look at the relationship between all three variables. Specifically, the effect of engine size, number of cylinders, on car, or rather the effect of car on engine size, type of car on engine size, on the fuel efficiency. So we're looking at a difference of a difference of a difference. So there's a difference between Audi and VW, and we're going to also look at if there's a difference between Audi and VW depending on the difference in engine size between the cars. Does that make sense? So that's called an interaction. So we're looking at the interaction between those two variables. But first, let's look at them separately and see if there's just independent effects. So let's call this model car model 1, linear model object with an input which has city fuel efficiency as a function of two things. So we're going to write our equation out like this. The y-intercept, the baseline, is added implicitly. We don't have to explicitly add that. We're going to add each effect just as a combination. So just as by plussing, just like we did before with the equation that I showed you in the lecture. So we can add make. Sorry, model? No, make. Make, which is Audi or VW, plus cylinder. And the data we want is mid-size cars. Okay, so that's the model. And let's look at that. So now we're doing what we did before in the lecture. We're looking at these things independently. Oh, sorry, I always do that, don't I? There we go. So because of this syntax, this plus here, make plus cylinder, so this means city fuel efficiency as a function of make and cylinder, looking at them separately. So what do we see? So what can we say about our fuel efficiencies from this model output? What's the first thing we look at? Yeah?
Oh, you don't use slow.
That's this one?
Yeah,
That's the first one we look at. So the model's significant.
yes. And it's, the more you drive Volkswagen, the better fuel economy. But
Yeah.
the more cylinders you get, the less fuel economy. Or the worse fuel economy.
Yes. But before we go that far, we should look also at the quality of the model. So before we sort of go digging around in the parameters, let's look at the R squared and see how certain we can be about our claims. So this is reasonable. It's explaining about 35 to 36% of the variance. And the model's significant. And then we can look at the parameters, and like you say, all else being equal, inferring to the baseline, you get about 22 miles per gallon. If you pick an Audi over a Volkswagen, you'll use more fuel. No, you'll get more miles per gallon. I keep getting this backwards. If you pick a Volkswagen over an Audi, because of the way it's coded, I'm going to have to go through this with you. If we pick a Volkswagen over an Audi, you're going to get 1.6 miles per gallon extra. So it's going to be more efficient. And as the number of cylinders increase, for every cylinder that you put extra in the engine, you're going to get 1.02 miles per gallon less. So you're going to get a less fuel efficient car. And they're both significant, those two predictors. This is general, so this is independent of, this is ignoring, so this is like what we did with our three-dimensional space. So an important thing to notice here is we don't just get make as a label here, we get make Volkswagen. So what does that mean? The way that LM works is, it takes all of your, if you've got a variable that is what we call a factor. So it's something that is a nominal variable, where you can categorize your items or your measurements into different categories, and the only thing that's different is the name. Then LM doesn't have any a priori reason to put them in any specific order. So if it's a number, then 1's lower than 2, and 2's lower than 3, and 3's lower than 4. We're drawing this through this multi-dimensional space. All of the stuff that we covered in lectures was all numbers. So the direction that we were going in this space all had a reason to it. There was all logic to it. But when it's arbitrary, you could just as easily draw the picture with Audi first or Volkswagen first, as you could with Volkswagen first versus Audi first. So what LM does is it puts the different levels of this factor, it's called, these different categories in, it puts them in alphabetical order. So because Audi starts with A, it'll put Audi first, and then after that it'll put Volkswagen. And so what this will tell you is the change from Audi to Volkswagen. So this is essentially doing a t-test between Audi and Volkswagen. Okay? And then it's running a linear regression on cylinders independently.
Just out of curiosity, if we had 20 makes of cars, what would it come out with them? It would
have 19 different parameters, and it would compare each one to the baseline, which would be Audi.
Yes. Okay.
So you can imagine that if you've got a lot of levels to a factor, you should set your factors up in such a way that so that you're comparing to the baseline that you're interested in this sort of linear model. Because we'll do t-tests relative to that baseline. So if you've got some baseline in your study, the simplest way to do it, and the way that I've always done it, is to put a little a in front of the variable name. And I think there's also a way, some sort of part of the function that you can type in that tells you what one you want to be the baseline. But I just have never been bothered with that, I just put a little a. So you can look that up.
So when it's categorical, they say that The order doesn't matter except for baseline.
Except for the baseline,
Yeah.
exactly. And that's because what we're doing in a linear model is we're modeling a straight line. So here you're modeling a straight line between 2 points.
And
2
it
points.
doesn't affect the order doesn't affect
No.
the outcome.
No, but you just won't get the information that you're looking for if you don't have the baseline that you want to ask your question relative to, if you have one. Okay? But that's not yet giving us the information that we want. The information that we want is the relationship between the two variables, the two predictors. So how do we do that? We do that by doing Gange, or multiplication instead of plus. And then that gives us both the effect of make, the effect of cylinder, and the effect of the interaction between make and cylinder. And you'll notice, first thing that you notice is the p-value. This is the good model, so we can look inside of it. What's the second thing you notice? Yeah, and what do you notice about that?
Pretty good.
Yeah, what about relative to the last model?
Better.
It's better. So we've improved the model by adding this interaction between these two variables. Okay, so now we've got that. We'll come back to that. But let's proceed as we have been. What do you notice about the predictors? If you compare it to the last model. So our estimates, our B's. Well, they're changed, right? So the intercept used to be 22, and now it's 20. The effect of make used to be 1, now it's 10. And that's because you're drawing a new straight line now. It's not the same line. You're drawing a straight line through a space where you're also accounting for the interaction between the two variables that you're making a prediction on the basis of. So that changes your entire model. But you still get roughly the same conclusion. And here, you get an estimate, which is your interaction. And my advice would be for interpreting these is just plot your data. It's the easiest way to interpret it. So you can sit there and bend your mind around what a minus means. But what a significant effect here means is that there's a different effect of cylinder on fuel efficiency depending on whether we're looking at an Audi or a Volkswagen. Okay? So, cylinder always matters, and the car model always matters. So engine size always matters, and the car model always matters. And if there's no interaction between the two, what we could suggest might be happening is, so this is the VWs, this is the Audis, and this is your city fuel efficiency, and this is your cylinders. Right? And so if Audi is always worse than Volkswagen, then you'll get fewer miles per gallon at the baseline. Right? So that would be here and here. And there's an effective cylinder, so on both. But if that effective cylinder is the same for both cars, different kinds of car, then that slope will be the same. Be like this. So imagine they're the same. I haven't drawn it perfectly. Right? So what that would represent is a very clear effective cylinder and a very clear effect of make at these, so this is this point and this point, but no interaction between these two variables. However, if we saw this, what would we say? So this slope is still going down, but it's less. What could we say then? Yeah?
Audi cylinders are more efficient.
Audi cylinders are more efficient, yeah. So statistically, that means that there's an effect of engine size, and there's an effect of engine size here as well. So overall, there's an effect of engine size. The effect of engine size is always to decrease fuel efficiency. There's an effect of car type. Audi, independently of cylinder size, has a worse fuel efficiency. But the effect of cylinder size, the effect of engine size, is less for Audis than it is for VWs. So if I'm predicting what the fuel efficiency of a car will be, and I want to buy, say, a new car with 12 cylinders, and my car has to have 12 cylinders, then what this analysis might tell me is I should get an Audi anyway. So that's an interaction. More extreme version would be is if, for some marvel of physics, they'd figured out how to make it such that larger engines had improved fuel efficiency. So this really shows you, makes it clear for you. This is very clearly an interaction. So here there might be no overall effective cylinder because they cancel one another out. But a clear effective type of car and the interaction, in which case, as the car engine gets bigger, Audi's the better choice. And Audi's probably the better choice anyway, because as soon as you start, it doesn't take long before Audi overtakes Volkswagen. So this is a really, really explicit and clear interaction effect. But the other interaction effect is also an interaction effect that can have meaningful consequences. So does that make sense? Do you have a feeling for that? So that's what we're looking for when we're looking for interactions, and we do that a lot. So here, for example, we might be looking at the interaction between region, fertility, and life expectancy. So in some regions, an increase in fertility, Northern Europe we saw, might lead to an increase in life expectancy. And for others, it might go the other way. And I find it very difficult, even for two variables, to interpret this sign, what the minus means. When you start getting three variables, it gets very confusing. So what I suggest you do is always make this sort of plot, and then you'll be able to interpret it by just referring to the figure. So you can say there's an interaction between engine size and make of car, and figure 1 suggests that this interaction is driven by a smaller effective cylinder on fuel economy for the Audi car. Okay, so let's do that. See which type of car it matters more for. So plot. City as a function of cylinder. Data equals, going to do something tricky here. Just make sure it works before I start explaining it. Yes. So what I've done here is I've chosen my data, but basically I'm using the same plot function. I'm using the, what do you call it, the tilde syntax. And the data that I'm using is a subset of the mid-size cars data set. We did subsetting before, where make is equal to Audi. And this is what our plot looks like. Let's make the VW plot and then we can see them both. And then we can interpret our interaction. And I think it goes the other way compared to what I was drawing. Didn't work because it says Volkswagen, not VW. Alright, so we're going to have some visualization issues that we want to tidy up again. I'm just removing a blank plot that didn't work. And those visualization issues are that we have to click back and forward so we can't really see. And everything's on different scales over here and over here. So what we want to do is get everything onto the same figure. So we'll do something similar to what we did with polygons. I think it's points. I'm going a little bit off script here. So try that. So now it's putting all of the data points on the same plot. So what it's doing first is making a plot and plotting the Audi data with cylinders on the x-axis, city fuel economy on the cylinders on the x-axis, city fuel economy on the y-axis, where the data is for Audi, and then adding some data points with the same XY structure and the data for Volkswagen. But we can't see which one's which. So let's fix that. By making them green. But we're missing some of the Volkswagen ones, and we're not getting all of the stuff up and all of the stuff down. So let's play with our X-lim and Y-lim again. And see what a good value would be. 10 to say 30. Sorry, that should be Y-lim. That should be 0 to 10. So our x-axis limits are 0 to 10. And our y-axis limits, something nice and readable, make it 10 to 30. We can adjust it if it doesn't look good. Or we make it higher. Feel like we're still missing some data points at the top. Zero cylinders is not that interesting anyway. And there you go. We can see all of our data on the same plot. And so you can see if you were to draw a line through here, that'd be lower than than the Audi one. And I've forgotten the syntax for it, but you can also draw the actual line. Can you remember that? I know it in
This line.
I know it in no line connects
you
the
mean
dots.
outline.
Yeah, abline,
Outline. Try it again.
abline. Let's see. It should be the formula, I guess. Because it's really easy in ggplot. No. We'll come back to that. We'll look that up and come back to it. We'll draw the lines on later, and then we'll be able to see which one's tilting down more. And then you make a plot like this, and you can also put your confidence intervals on the line. We'll play a little bit around with that. Base plot's not so good for this sort of scatter plot. This is where you really need ggplot. But that's a tidy text thing. And you can start to represent your linear models visually. And you'll be able to say what this interaction is driven by. But just at a guess, I would say it's the green one, which is your Volkswagen, which has a bigger effect of cylinder, would be my guess. But we'll talk about that after cake, and I'll look up the syntax for it.
Can you enlarge the window so we can see the last bit of the code?
That one?
We can see.
Oh, sorry. Yeah, it gets a bit long. So this is just the limits out here. That's the limits on the axis. Okay. Yeah.
To be sure, when you change the syntax from make plus cylinder to make times cylinder, you
Yep.
expand the model and you take the interaction into account.
Yeah, exactly. And in the old days in R, you had to do that explicitly. So there was never this times. So you'd have to say, I want variable 1, I want variable 2, and I want the interaction between them. And if you do want to do that, I can show you the syntax. So let's call this one car model 3, model 1, model 2. If you just wanted the interaction, for instance, and not each of their particular variables, you would go colon. So that'll be a model with just the interaction, not each effect separately and then the interaction. So we can look at that too.
And a completely other question, but you added the jitter to the
Yeah.
plot earlier.
Yeah.
When you do that and when you rerun the switch, you'll have another plot because it's made by coincidence.
Yeah.
Could you do something else? In theory, you might end up in theory with all the dots hitting the same spot. So
Yeah.
could you do something else? Could you expand
The jitter?
dots instead of adding this jitter? So that the size of the dot shows the number of times it's been run.
Yeah, there's a number of different visualization techniques that you can use. And one of them I mentioned was you could have a solid dot, and then you could have a very, very low alpha.
Ah, yeah.
And so that as these dots get plotted on top of one another, you get a darker and darker dot, and that looks nicer. The jitter one I use just as I don't know if I'd use that particular jitter one in the paper. I'd come up with some other interesting visualization strategy, and I'd suggest that you look up some visualization tutorials. But that's a good one for just checking stuff. Yeah. But this gives us the answer to the first question that you had about if you just wanted to look at the interaction, or what I interpret to be your first question. So here we get a significant model again. It's a worse model than the one with both individual effects plus the interaction. And the interaction is significant. And that's basically it. So last thing we do before cake, and then we'll come back and while there's a break, we'll look up the syntax for adding a line. Is we saw before that the R squared changed when we added the interaction. So what does that imply? That implies that we improved the model. So that implies that we went from a model that could explain, what was it, 35% of the variance, up to a model that could explain, I think, 42% of the variance. I'm just trying to find it. Yeah, 42% of the variance. So working within the null hypothesis testing framework, the first thing we'll ask is that significant? Is that a significant improvement to warrant looking at the one model rather than the other? Because you'll notice that we get different parameter estimates, we get different slopes for our effects, depending on which model we use. So it's important. So what we want to do is try to find the true model, the truest model, and then look at the parameters in the truest model, and only those parameters. So how do we do that? We can do some simple model comparison. So we've got our model objects. We've got car model 1, car model 2. Let's give this some more informative names. Car model and car model interaction. Let's run these just to get them in R. We're not interested in the summaries yet. In fact, we shouldn't be looking at the summaries yet, because we shouldn't look at the parameters until we know what the best model is. So let's do a comparison of those two models. We do that by typing ANOVA. So what we're doing is an F test. We're calculating an F statistic. So if you conceptualize R squared as how much do we improve the model over no information, or just information about the averages? So how much of the variance are we explaining? So R squared gives you how much the model improves relative to no model. So the variance, how much of the variance we explained. What ANOVA is doing is it's doing an F test where we're getting an F statistic by comparing the first model we looked at, which is the model without the interaction, and then the second model we looked at, which is the model with the interaction. So we're doing that comparison and getting an F value. And then we've got the F value, we can put it on our whale, and then take the area under the curve from that F value out to infinity, and get a P value. So that's the logic of what we're doing. So let's look. Car model and car model, so the two arguments, this is sitting there waiting for some arguments, and those arguments is all of the models that we've built. Car model interaction, and let's see if the interaction improves the model enough for us to say that it's significantly better. So in other words, if we get an F score that's big enough such that that F score was sufficiently unlikely under the null hypothesis that there's no difference between the two models. And it is. So our F value, this is what I want to draw your attention to. Our F value is 27 and our P value is very, very small. So if we want to get closer to the truth, we should include the interaction between cylinders and makes in our model. And now we can go and look at the specific parameters inside the model. So this is the kind of approach you can take to linear modeling, is think about all the models that you could build them, and then do this, and then stop when you stop improving. And then when you've done that, pick the best one, and then look inside of it. Yeah?
So, would we have to do comparison on pairwise? I mean, for some like we did here, we took the one without the interaction compared to the one with the interaction. And let's say we had 3 other models.
Yeah.
We would have the one is the baseline that we compare to, or how
Yeah. So you could have more. You could have one with just the interaction.
Yeah.
So we call these main effects. Car model, main effects, car model, interaction, and that's just the interaction, so that's not the ganger but the colon. And then with the main effects and the interaction. And don't worry about the summaries just yet. Okay, and then we'll do an ANOVA on all 3. And then we see what we get. So we've got model 1, model 2, and model 3. Oh, that doesn't work because they're not nested. Ah, okay. I'll come back and explain that. So that one's not going to work.
This is
So
the idea that
you could add extra interactions and extra variables, but what matters is that you've got nested models.
And what is nested?
And a nested model is one where you have. Do you have a good definition of nested models, Adela? No?
You're running models inside.
Yeah, it's the model contains. So each model,
Yeah.
the most complex model, all of the simpler models are contained inside of the most complex model.
Yes.
I'm not sure if that's formally 100% correct, so I'm going to look it up just to make sure, but that's my intuition.
So the problem with this example was that one of them was not.
Yeah, I think so.
Didn't contain the other.
I think so. I'm going to look it up though.
Yeah.
Yeah, I'll look that up for you. So you can only do this model comparison if you've got nested models.
Okay.
So where all of the simpler models contain the more complex. Sorry, all of the simpler models are contained in the more complex one.
All right. Yeah.
Okay? And so in this way we're building up models, trying to find out at which point we stop adding information by adding more structure.
So, would we be able to make a model where the predictors were different? I mean, does that make sense?
No, I don't. No,
No.
no, because then it's not nested.
Okay. Yes.
Yeah, exactly.
Yeah. All right.
Okay, so let's have a break and have cake, and we'll look up how to put a line in the figures.